Hello students, today I am going to discuss polarization. So before it, as we know that there are two types of waves. Transverse, longitudinal. Okay, so in case of transverse waves, the direction of oscillation is perpendicular to the direction of propagation of wave. Okay, in case of longitudinal waves, the direction of oscillation is always in the direction of propagation of wave. Okay, so now what is polarization? So polarization, it is a property of applied to transverse waves. Okay, so polarization gives us the, or it specifies the geometrical orientation polarization specifies the geometrical orientation of the oscillations. Okay, so it is a polarization is particularly applied to transverse waves, and longitudinal waves do not exhibit polarization. Okay, so it is a property of transverse waves. So transverse waves such as EM waves, such as light, radio waves, these exhibit polarization. Okay, so EM waves consist of coupled oscillating electric field and magnetic field, and which are always perpendicular to the each other. So basically, by convention, the polarization of EM waves refers to the direction of the electric field. Okay, so polarization of EM waves, what does it give? It refers to the direction of electric field. Okay, so here now we consider that if we have a consider a plane wave. Okay, so this plane wave is propagating. So this plane wave is propagating in the z direction, and its electric field E, that is oriented along positive x-axis. Okay, so then this plane wave is represented as E1 equals to epsilon 1 E10 exponential iota k dot x minus omega t. So let it be equation number 1. So such a wave is called linearly polarized along epsilon. So however, a general state of polarization can be described by a linear combination of two independent states. So we consider a second linearly polarized wave, and that wave is represented as E2 equals to epsilon 2 cap E20 exponential iota k dot x minus omega t. Let it be equation number 2. So here the amplitudes E10 and E20. These are complex numbers. Okay. So and there is a adequate phase difference between them. So the linear combination of equation number 1 and equation number 2 gives a general solution of the plane wave in the k direction, and is given by E function of xt equals to epsilon 1 E10 plus epsilon 2 E20 into exponential iota k dot x minus omega t. So this is our equation number 3. Okay, so this is a linear combination of the two waves. So in this so in the polarization we have three cases. So three cases arises here. Okay, so first case is linearly polarized wave. So in case of linearly polarized wave, the vectors E1 and E2 are in phase, or their phase differ by an integral multiple of y. Integral multiple of y. So then equation number 3, this equation, in this case when the amplitudes are in phase, or their phases differ by an integral multiple, then this equation number 3 is said to be linearly polarized, with its polarizing vector making an angle with its polarization vector making an angle theta, and theta is equals to tan inverse E20 upon E10. Okay, so and its magnitude E is equals to E10 square plus E20 square raised to power 1 by 2. And electric field of a linearly polarized wave so it can be represented as E vector, and here angle theta direction of epsilon 1 E1, and this is E2 and epsilon 2. Okay, so this is electric field of linearly polarized wave. Okay, so this is our first case, linearly polarized wave. Okay, so second one is elliptically polarized and third one is circularly polarized. Okay, so secondly we discuss circularly polarized wave. Okay, so in this case the magnitudes of E10 and E20 are equal and differ in phase by pi by 2. So if we write the linear combination EXT, and EXT is equals to E naught epsilon 1 plus minus iota epsilon 2 exponential iota k dot x minus omega t. So in case, so if we take the real parts of the equations, then we have Ex xt equals to E10 E10 cos k z minus omega t and Ey xt equals to minus plus E20 sin k z minus omega t. So if we scaling and adding these two equations, what we get? Ex square upon E10 square plus Ey square equals to E20 square equals to 1. Okay, so in case of circularly polarized wave, we know that E10 equals to E20 and let it be equals to E naught. Okay, so then this equation 6, becomes Ex square upon E naught square plus Ey square upon E naught square equals to 1. So this is an equation of circle. Okay, so the vector E naught has a constant length and traces out a circle at frequency omega. Okay, so such a wave is said to be circularly polarized. So you can see that here we have two signs, a plus and a minus. So here upper sign, plus sign, this plus sign gives a counterclockwise direction, and this negative sign, this gives us the uh, clockwise direction of the wave. So if we so this is a circle. Okay, so this is circularly polarized wave. This is x direction and this is y direction. Okay, so this is a EF of a circularly polarized base. So equation number 6, again look here at equation number 6. So if we see it clearly, if E1 0 and E2 0 are not equal, then this gives us an equation of ellipse. So which is our third case of polarization. The third one is elliptically polarized wave. Okay, so equation number 6 is Ex square upon E10 square plus Ey square upon E20 square. So this is equals to 1, and which is an equation of ellipse. Okay, and in this case, elliptically polarized wave, E1 and E2 have different phases and magnitude. Have different phases and magnitudes are also different. Okay, so particularly elliptically polarized wave is a special case of circularly polarized wave when the magnitudes of E1 and E2 are not equal, then it is elliptically polarized, and if the magnitudes are equal, then the wave is circularly polarized wave. So we can also represent it as diagrammatically. So elliptical, okay. So this is our, sorry, you can write again. Okay, and this is our electric field, and this is x direction and this is y direction. Okay, so these are our, this is all about polarization, and three cases arises. First one is linearly polarized, then circularly polarized, and third one is elliptically polarized.